Hi guys. So today we're gonna talk about um Stefan Maxwell equation and then how we can solve or guess for the rate of evaporation of any species or component. So we're gonna write out the equation. So we can have the driving force of I, and we want to find the change in the vapor component. So d yi over within respect to distance z. That would be to the sum of I equal one to this n as in like as many number of species total times we're gonna have y, so like molar yi times nj minus yj times ni over c and then dij. So let me explain each of these variables. So yi is the vapor mole fraction of species I, and then nj is total flux of species j, and then same for this vapor mole fraction of species j, and then total flux of species I, and then total concentration, and then binary diffusion coefficient. So when we're given three species, acetone, methanol, and nitrogen, we only need to derive two equations, dy1 over dz and dy2 over dz. It's just because y3 is just 1 minus y1 minus y2. So now let's start with dy1. dy1 would be I1 y1 times n1 minus y1 times n1 over c d11 minus plus y1 over n2 minus y2 over n1 over total concentration times diffusion coefficient of 1 and 2 plus y2 and plus y1 and 3 minus y3 and 1, since there are three species. So yeah, we times concentration with the binary diffusion coefficient of 1 and 3. And so this is 0, cancel out. And then so we do the same for 2. We have y2 n1 minus y2 n y1 and 2 over total concentration times diffusion coefficient of 1 and 2 plus y2 n2 minus y2 n2 times concentration times diffusion coefficient of 2 and 2 plus y2 and 3 minus y3 and 2 c times d2 3. And then we also cross out this one. So now that we've derived the Stefan Maxwell equation for dy1 and dy2, we can introduce a new variable, scaling variables, new or v. Let's just go with new. I asked AI and they use v, which I'm not sure why, but in class we use new. So new is equal to z over theta. So this theta is just the thickness of the tube or layer. So we would have z is equal to theta times nu. dz would be theta times d nu. And now we substitute that into our equation. We would have, let's just see. For example, let's do dy1 over, so dz is now d nu, and then I'm just going to move theta to the other side. So we'd have theta times, again, I'm gonna copy this down here so I don't have to rewrite that. And so essentially, Z is the theta is the total thickness. So this variable, and they're both meter, so this is dimensionless. So it's essentially comparing the scale or the ratio of the distance compare that the flux goes through compared to the entire length of the tube. So nu is gonna have the value from 0 to 1. And so when we assume nu is equal to 1, we would have something like dy1 over d nu, where nu is 1. So it would have equal to dy1 is just theta, y1 is just y1. So that's how we are able to cancel out all these numbers. And we would just have, let's just say when nu is 1, then everything is gonna follow the order of 1. So y1, y1, y2, y3 are like follow the order of 1. So that's gonna give us um this ratio or this comparison. So we can have N1, N is gonna be equal to concentration times diffusion coefficient over theta. And so um let's do guess for N1 and N2, okay? So we know that concentration is just pressure. Let's see, concentration is mole over volume. So the N over V. N over V is P V T V over N. N over V is gonna be equal to RT or equal to P over RT. So we're gonna have P over RT according to ideal gas law times the diffusion coefficient over the thickness. So now we're just gonna do, so since it's just a guess, this number don't really matter, so we're gonna assume atmospheric temperature pressure 5 to the power 5, and then the diffusion coefficient to be 5 or -5, and then RT, let's say R is 10 times the temperature would be 384.5 times the thickness, which is 0.24. This is gonna come out to be equal to 1 over, let me just get my calculator real quick. 1 over 788.4. So we're gonna make N1, both are, I guess, N1 and N2 equal to that number. So which would be, let me just round it up, 0.168 times 10 to the -3. So that's our initial guess, and then now we're gonna move on to Excel for a better understanding of this. So I'm gonna stop sharing my screen on my iPad. And I'm gonna share my screen on the computer. All right. So we're gonna begin with our Excel. I'm just gonna keep actually sharing my screen on the iPad so it can use the data there. So now we're gonna type down the coefficient diffusion first. So 8.48 over millimeters second per square per second. We're gonna change it to meters square per second. So that's gonna be 8.48 8.48 times 10 to the negative times 10 to the negative 6. And then we're gonna do the same for the 1, 3, A2, 3. So for the 1, 3, it would be 13.72 times 10 to negative 6 equal. And then same thing for this one, 19.91 times 10. Now we're going to move on to our other values. So we're going to do, let's say, pressure. The given pressure is 99.4 kPa. We're going to convert it to PA. So 9.4 times 10 to the fifth, 10 to the third is 999,400. And then for temperature, it would be 2 point be 328.5. And then our temperature, gas constant is 8.114. And then our concentration is 36.4. And then our N1 and N2. So we previously guessed that N1 is 1 equal 1 over 78.5.4, and then same for N2, 1 over 78.4. And then so we're gonna construct the graph, okay? Okay, so we would have, let's just do a series here first. We would have Bill series column start value with 1,000, and then this is Z. Oh, and then Z, we have Z is equal to max Z is 0.24 meter. Then we would have DZ, let's, since we have an increment of like 1,000, like increment, we're gonna divide it by 1,000. So we have 0.00024 as our increment, and then we're gonna do Y1 over here, Y2 over here, Y3 over here, and then DYI DZ, Y1, DY2 over DZ. And so we would have Y1 in our initial given Y1 is 0.319. Over here, it would be 0.589, 528, and then this one over here is would be 1 over minus this minus this. And then so now we're going to use our formula that we derived earlier for dy1 over dz. So we would have equal to n1 y1 times n2, but I'm going to add the dollar sign to lock it, minus y2 times n1. divided by total concentration times diffusion coefficient of 1 and 2, diffusion coefficient of 1 and 2. Then I'm gonna add the dollar sign for both just to lock in. And then we're gonna times it by y1 times n3 minus y3 times n1. So we can have y1 times n3, which is 0. So actually you don't need that. We're just gonna need the second part. So we have negative y3 times um y3 times what's y3? Oh, we have y3 times n1, and then don't forget to lock it. Divided by concentration times d13. And so how do we get the concentration? We just use concentration again is pressure over R and T. So it's gonna, that's how I get the concentration. I forgot to mention. And so now moving on to dy2 over dz, we would have y2 times n1 and then lock it, lock it, lock it. Times n1 minus y1 times n2, which is this, and then don't forget to lock it. And then divided by concentration times T12, and then lock both two, just in case. Plus, since N3 is 0, we're gonna do the same. Plus negative Y3 times N2. Y3 times N2, N2, Y3 times N2, lock, and then neg over concentration times D23. And then don't forget to lock it. And then so since Z is increasing by DZ, which is 0.00024, we're gonna do that here. Z times E. And then Z, we're gonna lock it. Just gonna drag it down, but I'm actually making a mistake right here. 1 second. I think I'm gonna supposed to write 15. So that has been fixed. Sorry, that was a little mistake. And I'm just gonna drag it down to 1,000. So that's how we have all of the increments. And then for y1, I'm just gonna do, so with the increments of dz, we can have y1 plus dy1 times dz times a little distance increment, which is 0.00024. And we would have 2 point, let me double check this. G6. I think I didn't, that's what I meant to write. All right. And then do the same thing for this one over here. Y2 plus dy2 dz times dz. And then y3 is just 1 minus this and this. And then this one, we're just going to track it down here. So sure. I'm not sure why this doesn't work. Let me, oh, I forgot to lock this over here. Lock, don't forget to lock the value. Oh, shouldn't be like. Now that works. And so now I'm gonna drag it down to 1,000. Oh, I think I made a mistake again. Let's see what's wrong here. Oh, I forgot to lock this. Guess you have to lock this value. Lock it, lock it. Okay, let's try it again. All right. Let's see if everything's. Yep, so seems like everything is right. So I'm not gonna do this. So Y1 Z. So it looks like everything's correct. So it looks like everything's correct. So I'm just gonna do Y1 at the distant, like at the lot at the end, distance Z, then Y2 at the end, distance Z. And then it's gonna C is equal to G 1002. And then this one would be H 1002. So you can see that this is inaccurate because Y2Z is not close to zero, and then Y1Z is negative. So, so now that we know that, see, like the sum, the skew, this, and this, they don't add up to one, which you know something is wrong. So now we can, uh, oh, yeah. So now the sum doesn't add up to one, so we know that something's wrong. So now we can use solver, a tool called solver, so that we can set an objective nearest closest to our initial guess of n1 and n2. And then so that's how we can get the accurate answer. So I'm gonna set objective to be this one, and then changing variable cell to this. Make unconstrained variables non-negative and solve. And after we do this step, we should get the accurate answer. I'm not sure why it's inaccurate. Let's just retry this. It's okay, I'll cut it out. Hi guys, so sorry. I made a couple mistake earlier. So so now I'm gonna do the solver again, just for a more accurate answer. I'm just gonna do home data solver, and then I'm gonna set my objective to be this one. And then I'm going to do a minimum value of by changing it to N1 and N2, and then unmark this, and then I'm going to solve, and it's going to take a little bit of time. And then so while we waiting for it to solve, um, I don't know, how do I show my camera? All right, 1 second. Should we zoom? Perfect. So that's how we do, you see that earlier, the value of y1 and y2 doesn't add up to 1, or it's like very close to um it's over 1, which shouldn't be, because we also have y3, and then all three of them could only add up to 1. So that was inaccurate. But after we use the solver where we we try to minimize it to the initial guess of our n1 and n2, and we have this final accurate version of y1 and y2. And so why does last question. So why does let me just pull up the question and unshare my screen. And I'm going to share my screen on my iPad. Let me change this. So when over here, 7 Maxwell equation, you a good initial guess about with scaling. So because imagine with the scaling, we are able to have an accurate guess or an idea or magnitude guess of our y1 and y2, just because this scale is like z over the total length. So we know that if this is 1, then d1 y d this is just equal to y1. So let's just say y1 is 3.319. We know that from 0 to the total layer, it can only change its value can only be changed within this scale. So from 0 to 0.1, that's the only, it helps us assume how much more fractions can change. So it gives us a good initial guesses for the fluxes of acetone and methanol. That'll be all. Thanks for listening.